Okay, so good evening, one and all. Today is the last day, so we have to cover a lot of things. So before starting today's session, just let me recall what we have done in the last session. So yesterday we learned how to perform these UV visible spectra calculation, then these ECD spectra calculation, then how to calculate the frontier molecular orbitals. Then we discussed about how to calculate the various chemical reactivity parameters by using the energy of HOMO and energy of LUMO. And then we learned how to perform NBO calculation, natural bound orbital calculation. And then we learned how to perform this stability calculation, how to check whether the optimization of your molecule was done properly or not. So that is what we covered yesterday. So in today's class, we are going to learn a lot of things. So first, I will talk about how to perform this scan calculation or PES calculation. So after that, I will demonstrate you how to calculate the salvation energy of your molecule. Then I will demonstrate how to calculate the bond formation or dissociation energy of your molecule. Then I will demonstrate you how to perform this IRC calculation, intrinsic reaction coordinate calculations. From performing those calculations, you can find out the transition state, so reaction path, all those kind of things. And then I will show you how to perform the DFT calculation at different temperature, pressure, and pH. Then how to use the multiple basis set for the calculation. Then I will demonstrate you how to perform the batch DFT calculation. And will also discuss about how to perform this periodic system calculation, because some of the participants, they want to do the DFT calculation of the 2D materials. I will show how to submit such kind of calculation. And also some of the participants are asking that how to perform these fluorescence spectra calculation, like emission spectra calculation. So I will show that one also. So maybe today I will take like 2.5 hours. So without further delay, we'll begin the session. Okay. So first we'll start with the this one, scan DFT calculation. Okay. So first try to understand like what is a scan DFT calculation. So why should we need to perform the scan DFT calculation? So what information we'll get from the scan DFT calculation? So this scan DFT calculation means you can also call it as like PES calculation. So PES is nothing but potential energy scan. And the full form of the scan term is like it is like strongly constrained and approximately normal. So that is the full form of that calculation, but it is usually performed to study the potential energy at different coordinates of your molecule. So by if you perform this scan DFT calculation, so it will help us to explore the potential energy surface of your molecule by systematically varying the specific geometric parameters. So geometric parameters means either it may be bond length or bond angle, dihedral angle. So by changing those parameters, so it will find out what is the potential energy surface of your molecular system. Okay. So by doing this scan DFT calculation, you can find out so what is like local minima. So local minima is nothing but stable conformation. And you can find out the transition state also, like energy barriers of your molecular system. So because these information plays like crucial role in understanding the reaction mechanism and the molecular behavior. So that is like what I'm telling to explain is like you can determine the geometries of your intermediate and transition state along the reaction coordinates. So it will also give the information about how the energy change associated with the different conformation of your molecule. Okay, so usually whenever you are going to perform this scan type of DFT calculation, so we'll use their coordinate, geometric coordinates. Like we have to choose either bond length or bond angle or dihedral angle. By using those parameters only, we are going to perform the scan calculation. It is very simple calculation. It will take some time to perform those type of calculation. But let me demonstrate now how to perform such kind of calculation. So I hope all of you are trying to do simultaneously with me. Okay, so those who are doing simultaneously with me, you just open the software. You just double click on your Gaussian software. So it will open the Gaussian window and the visualization window both. Let me click here. Okay. So now here you need to upload your optimized structure. So for this demonstration also we'll go with the ethanol only. So already we have optimized the geometry of ethanol. So whatever the optimized structure is there, you need to upload to perform the scan calculation. Optimized structure is nothing but logarithmic file of your geometry optimization calculation. So how to upload? Either you can just click on the file menu and then go to the open, otherwise directly just click on this open icon. Okay. So click on this open icon and then go to the folder where your logarithmic file is present. In my case, it is present in the desktop. So I will select this one and just click on the open. So it will open the optimized structure of ethanol. Okay. So once you open the structure, okay. So now, whenever we are going to perform these calculation, like frequency calculation, energy calculation, all those kind of things, we are like directly we are submitting the calculation, right? So here we have to give some kind of we have to define the coordinates. So what kind of coordinates you are going to perform the calculation? So let me show how to assign those coordinates. So before going to assign coordinates, you just label the atoms which are present in your molecule. How to label? It is very simple. You just right click, then go to the view and you just click on the label. Okay. See, so it will label the position of each atom which you are present in your molecular system. Okay. So later you will understand like why should we need to label. So without labeling also you can do that, but we have to give the exact position of those coordinates to calculate the perform the scan type of calculation. Okay. So now to define the coordinates, we have to use this reductant coordination editor button. It is very simple. Directly can just click on this icon. That's like icon which is represented with the R. Otherwise, if you're facing problem to find out this icon, it is very simple. You just keep your cursor on your structure, right click, then go to the tools option. So here you will get this option like redundant coordinates. Okay. So you will get this window. So by using this window, you have to define your coordinates. So what coordinates you are going to use to perform the calculations. So to set up the coordinates, first you need to click on this add option because we are going to define now. So to define the coordinates, first you just click on this add button. So once you click on this add option, so here it will be activated now. So here you have to choose what you are going to choose. See here you can select the Cartesian coordinates, or you can select the bond, you can select the angle, dihedral, like linear bend, out of the plane bend, undefined. There are different things are there. So you can choose anything. For example, if you choose like bond, you have to choose only two atoms. You have to define only two atoms. If you have to choose the angle, you have to define three atoms. If you have to go with like dihedral, then you have to define the four atoms. So for this demonstration, let me go with the dihedral. Okay. So I want to change that how the energy of this system is changes by changing the coordinates like these dihedral coordinates. So I will just select the dihedral. See, dihedral means it will give the four boxes. Now, if you choose like bond, it will give only the two boxes. We have to select only two atoms. Okay. See here. So now I want to go with the dihedral and now we can decide the coordinates. You just give the numbering of coordinates. Let me take these coordinates 1, 2, 3, 4. So now without labeling, it is very difficult to find out what is the position of this hydrogen, what is the position of this oxygen. So now we can easily find out. Now we can just give the numbering here. I'm going to consider these four. Not only these four, you can give any, okay? So there are many dihedral angle you can measure, like this also you can measure. So like this you can measure, like this you can measure. So there is a different, like here also you can measure it. Like 1, 2, 5, 7 also. But let me go with this one just for the demonstration. So I will give 9 here. Here I will just keep E8 and see it automatically it will select. The first one is the 9 and the second one will be the 8. So let me keep it as like 5. Then I will go this one 6. Okay. So now it got selected. So all the four got selected. It will update here. See now all the four dihedral atoms. So we are going to change now. So what we are going to change, we are going to rotate. So let's consider by rotating this dihedral angle. So how the energy of your molecule will changes. Let's consider how your molecule and you have to find out that which is the best conformation of your material. In which angle your material should be more stable. In that case, these kind of calculations are more helpful. So let's consider if you are going to rotate this bond angle. then how the stability of your molecules is changes. Even you can just find out by changing the bond length also, how the stability of your molecule changes. By changing the bond angle also, not only you can choose any particular bond, okay, and you can study that one. But for it is not possible to demonstrate everything, so that's why for demonstration I'm going to take only one. And let's consider you have taken this one. Similarly, if you want to find out the one more bond, like one more dihedral angle, let's consider this 7, 5, 1, 2. How the stability of your molecule changes by changing this one. You have to click on add button. Once again, it will add the one more list and you can select it here. Okay. So once you have given the coordinates, you just click on this add button here. You just click on this down button here. And here you have to choose the scan coordinates. There is option called like scan coordinates. Okay. Select the scan coordinate. So once you select the scan coordinate, you will get the two more option like take like step of the size. So like how much you want to rotate your dihedral angle. So now what we are going to check here, by rotating this dihedral angle, whether we can increase the stability of our molecule or not. Okay. So here let's consider, I just want to rotate it for like 180 degree. Okay. I want to rotate it like 180 degree. And let me keep it as like I want to rotate that 180 degree in like six step. I will give like six steps. So six steps means how many degree I need to rotate at a time? 30 degree, right? So 30 degree, then 30 degree 60, then 30 90, then 30 it will be 120, 150, 180. So how much? Now we just give the 30 degree. So otherwise if you want to rotate it only two steps, you just give the two take and here you have to give the 90 degree. First it will rotate 90 degree, then 180 degree. So otherwise if you want to rotate in three steps, here give the three, here you have to mention the 60 degree. Okay. So once you have given that, you just click on the OK button. So click on the OK. So now the parameter got set now. Okay. So now we can submit the calculation. So to submit the calculation, you just click on the calculate button. Click on the calculate. Then go to the Gaussian calculation setup. Okay. Gaussian calculation setup. And the job type. So once you have defined these coordinates, scan coordinates, automatically it will select the your job type. So here we have to choose the scan calculation. Scan is nothing but strongly constrained and approximately normalized. Okay, so that is the meaning of calculation. That is a type of theoretical calculation here. And here you can just relax. See here there is different coordinates. Is you can just no need to change. You just go with this relaxed redundant coordinate. No need to change anything here, and just click on the method. So method also no need to change. Just go with the default option. So whatever the things you have taken for your geometry optimization, you just go with this one only. Like ground state, DFT type calculation, default spin, B3LYP functional, 631G basis set, plus diffusion function, DNP polarization function, charge will be 0 and spin will be singlet. So no need to change anything. Then click on the title button. So let me rename it as like ethanol underscore scan. Ethanol underscore scan. Let me copy this one. Okay. And now we just click on no need to change anything here. Link generally here, no need to change anything. Okay. And even no need to change anything. You just click on the preview button here. So it will give you a preview of your input file. And here you have to give one keyword, additional keywords whenever you are going to perform this one. Otherwise, sometimes you will get error. Sometimes, okay, for example, you just run the calculation without giving the keyword also. If you are getting the error, in that case, you just give opt is equal to very tight. Okay. So first execute the calculation without any keywords. So if your calculation is going properly, then well. If you are getting any kind of error, then better you just give the keyword opt is equal to very tight. Once it is given, but this let me go the calculation without giving any keywords. And now just submit the calculation. Just click on the submit button, then click on the save button. So it will just give the name of your input file. Just control V. Already we have copied from the title page. Just click on the save button. And now it will ask you to submit the calculation to the Gaussian. Just click on the S button. So once you click on the S button, it will start the calculation. So now the calculation is going on. So this scan calculation will take time, but let me wait like how much time it will take. So like that, you need to submit the your scan calculation. It is very simple. No need to worry about that. So once you click on the scan calculation, it will start the calculation. So now the calculation is going on. So this scan calculation will take time, but let me wait like how much time it will take. So like that, you need to submit the your scan calculation. It is very simple. No need to worry about that. So once you click on the scan calculation, it will start the calculation. So So yeah, I mean, could you please expand scan once again, sir? So it is not possible, ma'am. Yeah, minimum actually already we are lack of time. So please go through the recordings. There is a question from Ankita. Could you please repeat the keyword? So keyword is like, let me write it. Meeting group chat. Opt is equal to very tight. OPT. You have to write it in a small letter. Yes, yes. So if you are getting error between like space, just remove that one. See, it was taking more time compared to our previous calculation. So this one was taking more time. And here I'm just showing for one dihedral angle. So like that, you can change it for like, check it how the stability of your molecule changes. So it won't show directly stability. It will give the energy value, how the energy is changing. As you rotate your molecule to the different like this dihedral angle. Let me, once you completed the calculation. So with the diagram, I will explain you how you can predict the whether which conformation is more stable. So, so those who are doing simultaneously with me, so write it in the chat box. How many of you are like submitted the calculation successfully? Is anybody facing any kind of technical issues? Only two? Okay. So I mean, it's okay doing three. So maybe it will take around 1 or 2 more minutes. So we'll wait until it finishes the job. So within that time, if you have any questions from day one to so far, you can just write it in the chat box because today is the last day. So whatever the doubts you have, you just can clarify today itself. Okay, it was taking a lot of time, so we'll wait. So if there are any questions, you can write it in the chat box. So there is a question from Samruddhi. So in docking studies too, we can get the most stable conformation. Then what is the advance of DFT calculation over docking studies? At Samruddhi, your statement is not correct. Okay. Your statement is wrong. You have to make a little correction to your statement. So because from by performing the docking studies, you won't get the most stable conformation. Okay. So docking studies only gives the information that so how the interaction between your protein molecule and your ligand molecule. So what kind of interactions are there? Okay. If you want to check that whether that conformation is stable or not, again you need to perform the MD simulation calculation. That is why we perform the MD simulation. Docking studies won't give the most stable conformation. So MD simulation will give. I hope it is clear to you. Okay. So in now, my case, the calculation was completed. Okay. I hope. So is anybody completed? So how many of you completed the calculation successfully? So those who have done, you just type in the chat box. Maybe it is still going in some cases because it depends on your system specification. Okay. So let me start the analysis part. So, okay, you just click on the yes button here and open the logarithmic file. Okay. So this is the structure after optimization. And see here, let me open this one. And now you can see here, it will give the different. Click here. See, it will give the different. So this is a structure. This is the initial structure. So this is the structure of your molecule after 30-degree rotation of this dihedral bond. So this is, see, this is after the 60-degree rotation. So this is after 90-degree rotation, 120-degree rotation. This is like 150-degree rotation, 180-degree rotation. Okay, but I will show it still properly. You just right click here, go to the results, and you just click on the scan option. So now the scan got highlighted. You just click on the scan option here. So now see here, it will give the how the energy is changing. So this is your initial structure. So what is the energy of your initial structure? That is minus 155.058. Okay. So like if you click here, so this is the energy of your initial state. So once you rotate this dihedral angle to the 30-degree, so it was energy is this much. Okay. How much? Minus 155.0571. Okay. And if you go here, again, it was energy is this much. Energy is increasing, right? So here the energy is increasing. It's this point. Again, if you rotate to like this is for like 30-degree rotation, this is for the 60-degree rotation. So what information you will get it here? So if you rotate this dihedral angle to like 30-degree, so it will decrease the stability of your molecule. And if you rotate that dihedral angle to 60-degree, again it will decrease stability of your molecule. If you rotate 90-degree, so compared to your initial, the stability will be less, but compared to the 30-degree, it will be like still even not that much stable compared to, but this 160-degree rotation, it will be better. And again, if you rotate it to like 120-degree, so this is the energy of your molecule, this much, like 155.057. Even still, it is not less compared to your initial position. And again, it was like at 150-degree, then this is like 180-degree. So as you rotate this dihedral angle to the 180-degree, so the energy value from 155.05792, it was increasing to this much. So 155.05569. So the stability is decreasing. So like that, you can do the analysis part, like how the stability of your molecule increases. Similarly, if you click here, see, so it is like proper graph. So the scan RMS gradient. So now if you rotate 30, this is the initial position. If you rotate 30-degree, so it was like increasing, decreasing, increasing, decreasing, like you are getting. And if you want to calculate different parameters, right click. Even you can just click on the properties. So now you can just choose like you can properties here, not properties. Let me, there is an option. Let me here, properties, other plot. I can click here. Is it extra properties? Close. Yeah. So this one is like plot molecular properties. So if you click on this plot molecular property, there is like different option. You can choose the bond also now. You can choose the angle, three angles here, and you just click on the OK button. So it will plot for that one. How during that angle, how the energy is changing. Again, right click, and if you sorry, you just go to the plot here. Again, you just click on the plot molecular property, and you can just select. Let's consider how the energy changes by changing the bond length of this one and two. You just select one and two, and you just click here. And if you click here, see, it was like scan coordinates. It was going. So energy changes. Okay. So like that, you can analyze the different parameters according to your calculation. So I will just stop this one with this one, and you can use according to your requirement. You can do the analysis part. I hope it is clear to you. So let me close this one. Yeah, I will close this one also. Okay. So now we are done with the scan calculation. So let's move on to the next topic. Now I will demonstrate you how to calculate the salvation energy. It is very, very simple. You already know how to do the salvation energy. I just want to clarify one thing to you. So first try to understand like what is salvation energy. So salvation energy is nothing but the change in the energy. So when an ion or molecule is surrounded by the solvent molecule and it becomes the solvated, right? In that case, how the energy changes, that energy is known as the salvation energy. So it is the measure of interaction strength between the solute molecule and the solvent molecules. So whatever this energy is changing, because let's consider very simple. So you have some compound sodium chloride, and you have one beaker. In that you have taken on glass, in that you have the water, and now you are adding that salt to that water. So now you are adding here, your salt is a solute and your water is a solvent. So when you add the solute to the solvent, there is some amount of change, there is change in the energy. So because of the interaction between the solute and solvent molecule. So whatever the energy change is there, either it may be the positive energy or negative energy. So whether it is positive or negative, it depends on the nature of your solute and solvent molecule. And also what kind of interaction is there between your solute and solvent. Okay. So now the question will come. So what does it indicate? If the salvation energy is negative, what does it indicate? If the salvation energy is positive, so what does it indicate? For example, let's consider you are getting the negative salvation energy. It means that when a solute dissolve in a solvent, the energy is releasing. It is going to release the energy. Let's consider, for example, if you are from chemistry background, I think you are all like aware with the NaOH, right? So take water, and if you add NaOH to the water, so it will become like hot. Your glass, where whatever the glass where you have taken, you will feel the hotness. So because it is releasing some amount of energy, okay, and that energy is negative because it is exothermic process. Okay, so it will tell us that that reaction is exothermic in nature. So it indicates that the system becomes more stable after the salvation. Okay, so that is the how you can correlate. One is like the energy is releasing. The energy is releasing means it is exothermic in nature. If it is exothermic means your system is becoming more stable once it dissolve in the solvent. That is the meaning of the negative salvation energy. Okay, so then what does the positive salvation energy increases? Okay, so positive, like consider you are going to dissolve now solute molecule inside your solvent. So when a solute dissolve in a solvent molecule, if the energy is absorbed, okay. So energy absorbed means let consider you are taking some water and you are adding some compound. When you dissolve it, you will feel the like coolness. Okay. So means it is absorbing the energy. Such kind of reactions are known as the endothermic reaction. Those are like very basic things. Okay. And it indicates that the solute solvent interactions are weaker than the either solute solute or solvent solvent interaction. So such kind of salvations are less preferred. Okay. So it indicates that so your molecule is becoming less stable after the salvation. That is the physical significance of the negative salvation energy and the positive salvation energy. I hope it is clear to you. And by depending on that salvation energy, you can find out that before going to the experimental studies, theoretically you can find out that so whether it will soluble or not in that solvent, particular solvent. Okay, I hope it is clear to you. So now, and it is calculation of salvation energy is also very easy thing. No need to, let consider if you want to find out the, there is a, you have a compound A and you have to find out what is the salvation energy of compound A in presence of like DMSO. With respect to DMSO, what is the salvation energy? So the same thing, what you need to do, you have to draw the structure of your A, compound A, and perform the geometry optimization in the gas phase. So that will give the total energy of your molecule in the gas phase without any solvent. The same thing, you have to perform the geometry optimization of the same molecule in presence of that respective solvent. So then it will give the energy of that molecule in presence of that solvents. Now just take the difference between these two. Okay. The difference between these two will give the what is the salvation energy of that molecule in that respective solvent. So let's consider for this example also I will go with the ethanol only. Already we have done the optimization of ethanol, right? So previously we are on the day two itself we have done the optimization of ethanol in gas phase. So now I'm not going to repeat it once again due to the shortage of time. So now just I'm going to perform the geometry optimization of the ethanol in like solvent. In presence of solvent, I'm going to do that one. So let's see how much energy I will get it now. So very simple. What I will do the same optimized compound, same log file. You just click on the file, go to the open and select your logarithmic file of optimization calculation. So this is the optimized structure in the gas phase. So now you can calculate by using this same structure, you can calculate the energy of your molecule in presence of any solvent. Whatever the solvent you want of your choice, you can choose that one. So let me right click. Sorry, calculate. Go to the Gaussian calculation setup. Now just job type, you have to choose the optimization. No need to change anything. So method, everything, no need to change. The only thing is directly can just come here. So ethanol opt, I will just give ethanol opt underscore. Let me do either in any one of the solvent. Opt underscore. Let me do it like methanol. So methanol. So like we are taking ethanol and methanol. So when we mix both ethanol and methanol, how it will react, we can find out it out. Whether it will increase the stability or decrease the stability. So how we can find out it. Let me copy this one. And I just click on the salvation. You just go here. You have to choose the default and choose the methanol. Let me find out where it is. Yeah, methanol. Okay, that's it. You just click on the preview and you can just submit the calculation. Submit, save. Just give the name of your input file, Control V, and you just click on the save button and submit the calculation. So, okay, it will take around 30 to 40 seconds to finish the calculation. So let me check how much energy difference you will get, whether you will get the negative energy or positive energy. So here there is a question from Ankita, pop is equal to full, not required. See here already it will took by default. So because here, whatever the structure we have taken the logarithmic file of our previous optimization calculation. So already we have given that opt is equal to, sorry, pop is equal to full, automatically it will take, no need to give once again. See, in my case, the calculation was done. So now you just open your output file. Okay, you just click on the S button and open the logarithmic file. Click open here and now just right click and go to the results and go to the summary. It will give you what is the energy of your ethanol in presence of solvent is equal to methanol. So how much we are getting here? So minus 155 point, just to take the 4 decimal or otherwise take all the decimals. Then we can find out the proper difference. 0.63657. This is the energy of your molecule in presence of methanol. So this is the optimized structure. So without any one, just find out what is the energy we got in gas phase. Right click results and you just click on the let me, I think input file it is. So I'll just close this one and let me open that logarithmic file of our calculation, gas phase calculation once again, and we can find out the energy. So in my case, I'm getting the minus 155.06. Then go to the file, open. Let me open this ethanol underscore log file. This is because I want to note down what is the gas phase energy. Right click on the results, go to the summary. So here we are getting the minus 155.05 7984. Now take the difference between these two. Okay. So how to take your energy in the gas phase minus energy in like a gas phase with respect to solvent, you just take the difference here. Let me calculate it. You can calculate here because the energy of your system in presence of solvent is 155.06 3657, right? 3657 minus in gas phase energy is 155 0.057984. And the energy difference you are getting is minus 0.005673. Okay, so that is the energy difference. If you take the energy difference between the energy in presence of solvent and energy in gas phase, so that will give the salvation energy of your ethanol with respect to methanol. So that we are getting the negative energy. So negative energy means, so the interaction, whatever the interaction it is forming, solute solvent interaction, it is more stronger, and the structure is becoming more stable compared to the your solute. Like if you take pure ethanol, and if you take both mixture of ethanol and methanol, that is more stable compared to the pure either ethanol or pure methanol. I hope it is clear to you. So like that, you can find out the salvation energy of your molecule in any solvent. I hope it is clear to you. So let me close this one. So do you have any questions so far? So if you have any questions, please write it in the chat box. So there is a question from, so what if the solvent required is not present in the default option? Then you have to select the other option. So let me show it here. Let's consider. Uh, so let me go with this methanol only. I'm not going to I will show, draw the methanol structure, right click, go to the calculate, Gaussian calculation setup. Let me go with optimization method. So let me go with the default. I don't want to change anything. Just I want to show the salvation. Come to the salvation here. So here instead of default, click on the default, and here you have to choose if there is no solvent is there, your required solvent, you just click on the other and then just give the name of that solvent. That's it. So I hope it is clear to you, Ankita. So there is a question from Amine, got an error from scan calculation. So if you have got error means I think something you have did mistake while assigning the coordinates. So that's why you are getting the error. So you just go through the recordings. Okay. Now just let me, so if you have any questions, please write it in the chat box. Any questions? So if there are no question, everything is clear, then type Y. So we can go for the next calculation. So even, yes, even there is some mistake in your proper like numbering also, like if you did not assign properly, and it will give. Otherwise, sometimes you will get the error. Sometimes you will get like link one error. That is due to maybe the improper, due to the unavailability of the sufficient amount of the memory also. You have to then just increase the memory also. So now let's go to the how to do the calculation of this bond formation energy or bond dissociation energy. So because actually the thing will be different. Bond formation energy means the amount of energy is required to make some particular bond. Okay. So bond dissociation energy is nothing but the amount of energy is needed to break that bond. But no need to calculate both bond formation and bond dissociation energy separately. If you calculate one, automatically we'll get to know the one more thing. Let's consider you need like 5 electron volt to break one particular bond. It indicates that if you need 5 electron volt to break that bond, you need that much energy only to make that bond. So that is the meaning of that. Okay. So now let me show how to calculate this bond deformation energy. Okay. So it is here you have to perform like 3 calculations. How? Let's consider if you want to do the let me take other example here. Let me close this one and open the software once again here. Refresh. Okay, so let me open the Gauss wave here and set up. Right click. Yes. Okay. So let's consider if you phenol. Let's consider the phenol as an example. So benzene, it is connected to the hydroxy group, OH group. So now let's consider if you want to find out the bond formation energy of that OH. Okay. So how much energy is needed to break that OH bond, or how much energy is needed to make that bond. So in that case, what you need to do? So first you need to draw the structure of your phenol molecule and perform the frequency and like optimization and frequency calculation. So it will give the, so what is the total energy of your molecule? Okay, otherwise you can just perform the energy calculation also. So to get the more accurate result, you just perform the optimization and frequency calculation. And now to calculate this bond breaking or making, so you have to take the radical. Again, you just draw the structure of phenyl radical and you can calculate the energy of that one. Similarly, you need to uh, draw the structure of your like hydrogen radical and you can calculate the optimization and frequency calculation for that. And now you know the what is the energy of your phenyl, you know the what is the energy of the phenyl radical, then you know the what is the energy of hydrogen radical. So now you just very simple formula. So bond dissociation energy or bond formation energy is nothing but energy of your product minus energy of your reactant. So here the product will be the your phenyl radical and hydrogen radical, right? And your reactant will be the phenol. So now let me show how to do that one. So let me, I don't know how much time it will take. Let me do it here. So now draw the structure of phenol. How to draw the structure of phenol? Go to the view option, activate the builder button, then click on this ring fragmentation button. Okay, select the benzene ring. So draw it here. So this is the structure of benzene. And now just, uh, and these are the hydrogen, replace one of the hydrogen with the hydroxy group. So you just click on this element fragment button and then select the oxygen here. And I want to highlight this. You can just click here. So see, it was added the oxygen. And now I want to make it proper aromatization like alternative double bond and single bond, like equivalent type of representation. What I will do here, I'll just click on this bond option here and you just select any two atoms here, make it a double bond. Okay, then click OK. Then select these two, make it single bond. Then select these two. I think previously last class or before last class, someone asked like how to calculate the optimize the radical. So in this step, you will understand. Okay, just select this one, click here, again make it as a single bond here. Make it a double bond. Okay, so make it single bond. Okay. So this is the structure of phenol, right? So now before submitting the calculation, you just perform the clean your structure. You just click on this button, clean. So now the structure got cleaned. So now we just perform the frequency plus optimization plus frequency calculation for your phenol molecule. Okay, first you have to calculate the overall energy of your reactant. So now we are going to find out the what is the amount of energy is needed to break this OH bond. Okay, so but we are going to take the reactant as phenol molecule. So you just perform the calculation here. Now just go to the calculate Gaussian calculation setup, select your optimization frequency calculation directly, and here otherwise you can go with the energy also because we want energy, and if you want like more accurate then you just go for the optimization plus frequency both calculation. So what I will do it here, optimization plus frequency calculation here, and yeah, minimum state, no need to change anything here. Otherwise, just to reduce the, because I just want to show the difference, just to reduce the time, I will go with the uh, optimization. Otherwise, optimization frequency calculation. Yeah, let me just go with the optimization. Okay, just to reduce the time. Otherwise, because if you calculate both one, it will take more time. Otherwise, if you want more accurate results, you can go. Otherwise, let me go. It may take another 1 or 2 minutes extra. Go with the opt here. No need to change anything here. You just click on the methods, and here let me go with the ground state. And this one is DFT default spin B3LYP. Let me go with 631G. Go with the plus, go with the D, go with the P. Okay. So charge is 0, spin is singlet. Okay. And now just click on this title here. So let me give a phenol underscore opt. Okay. Then just copy this one. Control C. No need to change anything here. Just click on the preview button. And now here you just give the pop is equal to full. And click on the update button. And just click on the submit button. Save. Then give the name of your calculation, Control V, and just click on the save button. Yes, now it will start the calculation. So now the geometry optimization and frequency calculation of uh, phenol molecule is going on. So once it is done, now we need to model the structure of phenyl radical. The only thing is we have to remove the hydrogen from there. That's it. And we have to perform the same type of calculation for the phenyl radical. And the next time we have to plot, take consider only the hydrogen radical, and we have to perform the geometry optimization for that. And then just apply your simple formula and take the difference between these two. It will take more time. We'll wait. So if you have any questions, you can write it in the chat box. So I hope you are doing simultaneously with me. Yeah, now the frequency calculation is going on. Otherwise, just if you want to reduce the time, you just for the practice, you can directly go with the energy also. But if you want to get more accurate result, you just perform the both optimization and frequency calculation. Next for the radical, let me go with the directly with the energy as because we have to save the time. So for the phenyl radical and hydrogen radical, I will directly go for the optimization calculation. I'm not going to consider the frequency calculation. But make sure that if you are going for the your work, you have to, for example, for reactant, if you are taking the optimization and frequency calculation for the your product, also you have to use the same parameters. You should not change the parameters. So whatever the parameters you are going to use for the reactant molecule, you have to use this. You need to use same parameters for the product also. So in this demonstration, as it is taking a lot of time, just to save time, I'm just going for the energy calculation for the product molecules. So still the calculation is going on. So within that time, if you have any questions from day one, you just write it in the chat box. So is anybody completed the calculation? So I think this error is due to the some mistake in the input file. So minimum, you just check it your input file properly and you just submit the calculation once again. So if you are getting this kind of error means there is some mistake with your input file. So just to see the difference in our previous molecule in ethanol, So we have how many atoms? CH3, 4 plus CH2, 3 plus 7 plus OH, 9 atoms, right? So 9 atoms. In this case, we have the 13 atoms. So there is an increase of 4 atoms. Just increasing the 4 atoms, see how much difference in the time. So as the number of atom increases, the time needed to perform the calculation also increases. So that's why, so in the demonstration, we are not going to take any kind of like a bigger molecule. Otherwise, you can perform the same, you can use the same methodology for all type of material. Either it may be organic molecules or aliphatic compound, or either it is metal complexes, either like organometallic or like inorganic metal complexes. You have to follow the same procedure. And even for like, there is a slight difference when it comes to the periodic boundary condition system, like periodic system, like 2D materials. 90% it will be same, only there is a change of like 10 to 15%. I will show that one, what is the changes. Okay, it was taking too much of time. Yes, yes, you can do that one. You just click go to the process option. If you want to pause the calculation, you just go to the process and you just click on the pause. And if you want to stop in between, you just click on the kill job. Otherwise, you can click directly this button also. I think this is a pause option here. You can just click that directly this one also. I think this one and this one I have to check. So this is to start the calculation. I think this one is to stop the calculation, I think. So let me, because already it was like 50 to 60% completed. So let me finish that calculation. Otherwise, again, I need to give the energy calculation. Even for directly, if I go to the energy calculation for phenol also, I think it will take like 5 to 6 minutes for the optimization. So for frequency, it will take more time. So let me wait. So, okay, so within that time, why to waste the time? So within that time, let me explain. So why should we need to perform the DFT calculation like at a different temperature, pressure, pH? So what information you will get, then how to do that. So let me talk about the theory part. Later I can show it in a short period time. Okay. Now let's try to understand, because now whatever the DFT calculation we are going to perform, so it is at the room temperature, unlike atmospheric pressure, like 1 atmospheric pressure. Now let's consider if you want to perform the same DFT calculation at different temperature, or if you want to perform at like different pressure, higher temperature, higher pressure, or lower temperature, or lower pressure, or if you want to perform at like different pH. Okay. How to do that one? And first you will get the question like, why should we need to do a different? Because by performing DFT calculation at different temperature, okay, so you can determine the what is the change in the entropy. Okay, what is the change in the entropy of your system? What is the change in the enthalpy of your system with respect to temperature? Okay. So which provides the information about the thermodynamic stability of the your system or your reaction. How thermodynamically it is stable. Like if you want to find out that whether that is thermodynamically stable or not, let consider usually for material to study the thermodynamical stability, we'll do the TGA, DSC studies, right? And if you want to check that, so whether your material is thermodynamically stable or not, until at what temperature it is like stable, then you can perform the DFT calculation at different temperature and you can correlate with your experimental studies. Let's consider first you need to perform the geometry optimization of your structure at the room temperature and note down the energy value and now just goes on increasing the temperature. Now let's consider first you have done at like 298 Kelvin. Now perform at the 350 Kelvin. Then perform the geometry optimization. Just check that energy, how much energy. So there is no change in the energy. It indicates that even at like 350 Kelvin, your material is thermodynamically stable. Let's go for the 400 Kelvin and perform the DFT calculation. Then compare the energy value. If the energy value is same, then it indicates that at 400 Kelvin also your material is thermodynamically stable. So if there is like slightly, if the energy value is decreasing means slightly as the temperature increases, the stability is slightly increasing. Let's consider you have did the calculation at like 800 Kelvin and there is the energy, okay, and the energy value is increased. Let's consider compared to your gas phase energy, the like sorry room temperature energy, like 800 Kelvin energy is more. It indicates that energy is more means less stable, right? So the stability of thermodynamical stability of your material is decreasing. So like how we can correlate, it is all about how we are going to correlate these your experimental data and theoretical data. And you can also study how the vibrational modes changes with the temperature. You already know that, right? As the temperature increases, the vibrational mode also changes. The vibration, the speed between your vibrational level also increases. Okay. So from that, by studying the how the vibrational mode changing in your system, you can study how the thermal conductivity and the specific heat of your system is changing. Hope it is clear to you. As the thermal conductivity increases, like vibrational modes like change the temperature, like vibration is more, automatically the thermal conductivity and the specific heat of your system will increases. See how you can correlate by doing this calculation. You can correlate with the thermodynamic stability. You can correlate with the thermal conductivity, right? You can correlate with the specific heat of your material, and you can just by like optimization. So after optimization, it will give the what is the specific heat of your system if you perform optimum frequency calculation. So at a different temperature, you can find out what is the specific heat of your system. And even you can calculate how the activation energy of your reaction changes with temperature. See, as we know that, right? The activation energy, let's consider if you want to perform on reaction. If you want to perform that reaction and you have to find that what is the suitable temperature to carry out that reaction. And in that case, you can just calculate the what is the activation energy of that reaction at room temperature and then goes on increasing the 290 Kelvin. Let me consider round figure 300 Kelvin. Then go for the 350, 400, 450, 500. So then you can find out that which temperature is more suitable to complete that reaction as soon as possible within short span of time. So you can calculate those kind of information. And even you can find out the relation between the pressure, volume, and temperature for your material. So how the relation is changing with respect to these three parameters. Okay. Even you can determine how the reaction energy and the barrier changes with respect to pressure. By changing the pressure, how the your reaction, because you can alter the rate of the reaction. Okay. Kinetics of the reaction by altering the temperature and pressure, right? So that is a well-known like basic thing. So even you can study the change in the band structure. Like for example, you are going to perform these 2D materials. You can find out how the change in the band structure and density states under the different temperature and pressure condition. So you can see calculation is very simple. You just give the parameter, it will do the calculation. The where it matters is like how you are going to correlate these theoretical information, this number, because here you will get only the number. Even it won't give any kind of theoretical information. It will just give the numerical numbers. By using those numerical numbers, how you are going to correlate with the theory part, and how you are going to correlate the theory part with your experimental data. Okay, that is completely depends on you and your like your area of interest, what exactly you are going to focus. So that's why we need to perform the DFT calculation at different temperature and pressure. So far we have done at the room temperature. Now we may get the question, then how to do that? How to perform the DFT calculation at like some higher temperature, lower temperature, or higher pressure or lower pressure? Even how to calculate the like even you can perform the DFT calculation at different pH. If you want to maintain the basic condition, if you want to maintain the acidic condition, you can just give change the pH value. You can specify the pH value, and you can calculate what is the energy of your molecule at that specific pH. You can do that one also. And what is the stability also changing of your molecule with that specific pH. You can do that one. It is very simple. The only thing is you have to make some small changes during your uh, this one input file generation. Okay, so now let me show before this. Once this calculation was done, I will show you. Otherwise, let me show now itself. So for that, let me very simple. Before that, I need to explain you how to prepare the input file. For example, now we are submitting the calculation through Gauss view, right? So now we are drawing the structure in the Gauss view, and we are preparing the input file. Then we are submitting the calculation in the Gaussian. So let's consider if you are using like Gaussian 16 version. Okay, or if it is like 19 version, if you want to directly submit the calculation without using the Gauss view, then you have to prepare your input file manually. Okay, so prepare the input file manually, you can directly submit that calculation to the Gaussian. So let me show now how to prepare that input file manually, then how to change the specify like different temperature, pressure, and pH in that. So let me minimize this window because it is taking more time. Let me wait for another 5 to 10 minutes. If you take more than that, then I will cancel this calculation. Then I will take some smaller molecule, any one smaller molecule. Let me try with ethanol only. So because already we know the what is the overall energy of ethanol. In that case, we go for the OH bond in ethanol, ethoxide ion. Yeah, actually that is the best option. I don't know why I choose this key now. Okay, let me minimize this one. Otherwise, keep it like this. So here, yeah, so there are already have there some input files are there. Let me open those files, any one input file. See, so these are the methane molecule. So how I have prepared the DFT, these are the different input file. See, this is the input file for the energy optimization calculation at 298.15 Kelvin at 1 atmospheric pressure. So this is the input file at 400 Kelvin at 1 atmospheric pressure. So this is the input file at 400 Kelvin and 2 atmospheric pressure. But let me open one thing and just let me show how to, let me go with this one. See, here's Gaussian. Let me open. So right click, open with Notepad. Open with Notepad. Otherwise, open with Notepad plus plus. Open with Notepad plus plus. See, and this is how your input file looks like. So whenever you are going to submit the calculation directly by using the Gaussian, so you have to prepare it like this. So just open your Notepad, or you can just prepare this file using Notepad or Notepad plus plus. Very simple. You have to write first line. This is first line. So this is common. Percentage symbol CHK. CHK means checkpoint file is equal to. So you have to give the name of your molecule. Now I have taken the methane molecule. That's why I have given the CH4.CHK. For example, you are going to calculate for the water, then you can give H2O.CHK. Otherwise, if you want to give some other name, you just give your name dot CHK. So it will save the, after the calculation, it will save the like checkpoint file. And the second thing is like percentage MEM. So it indicates that memory, how much memory you are going to use for this calculation. You just give 6M, otherwise you can just give the 2 GB. Like if you want to give the run calculation faster, you can assign the 6 GB. Okay. Like 2 GB, 1 GB, 3 GB, or you can go with this one also. And the third line, you have the information about the percentage N process shared. It indicates that number of processors you are going to perform this calculation. Okay, so how many processors you are going to perform, and just in this file I have given the 2. So if you want to increase, if you want to run the calculation faster, in that case you can just increase the number of processor. But make sure that before giving this number, you have to check that how many processors are available in your system. Let's consider in your system there is only 4 processor, but here you have given the 6 processor, then you will get the end up with the error. Okay. So let's consider in your system you have the 16 processor. In that case, you can just give like a 10 to 12 processor. Otherwise, if you give directly 16, so you can't do another like other task in your system. It will do your system will hang. So in my case, I have like 16 processor. Let me go with the 10 processors here, and I will just go with the 6. Okay, that is fine. 6M. Otherwise, you can give the this is more than sufficient for this molecule. But if you are going to take larger molecule, very large molecule, better you just go with the 2 GB. And below under you have to give this hashtag symbol, then give the space, then you have to give what kind of functional you are going to use. Okay. Here GEN indicates that generic term, like generic type of calculation. Otherwise, if you want to use like specific basis set, you can give like 6311G. And if you want to use this a diffusion function and polarization function, you just mention the plus. In the bracket, you just mention the, let me show it here. Like if you want to go like 6311G, just type 6311G and plus, that indicate plus indicates the your diffusion function. In the bracket, you have to mention the your polarization function D, comma, P. See like that. You can mention like this. Otherwise, you can, if you want to go to the generic calculation, you can just mention like GEN. So by default, it will choose the normal, this one. And you have to like, depending on the calculation, you have to mention this sudo is equal to read, and this one if gfi input file, that is like input file, in which format we are going to save the input file, that is like gf input file, and what kind of calculation you are going to do. So now for this molecule, I am going to perform both optimization and frequency. Give the space, give the optimization opt, space for frequency calculation freq. For example, if you want to perform the nmr calculation, give the nmr. If you want to perform the uv calculation, then give the energy. Okay. If you want to perform the scanning calculation, just type the scan. You can just write it here. And after that, you just give the space, enter. Once again, enter. You just give the enter here. Then you have to give the name of your compound. It is like methane. So that's why I have given the CH4 here. I think still it is running. Okay. And just again give the enter here, enter, then again enter. Here just you mention the 0 and 1. So what does it indicate? Here the 0 indicates the charge of that your molecule. So it is like neutral molecule. That's why I have given the 0. If your molecule is like negatively charged, then mention -1. Okay. If there is like -2 charges there, you have to mention -2. And then give the space, then give the, this 1 indicates the multiplicity, spin multiplicity, whether it is singlet or doublet. If it is singlet, you just give 1. If it is doublet, mention 2. If it is like triplet, mention 3. So below that, you have to mention all the atoms which are present in your molecule. So there are total how many atoms are there? Methane, there are 4 atoms, right? 1 carbon and 4 hydrogen. And then here you have to provide the coordinates along the XYZ direction. So how the coordinates are changing along the X and Y direction, you can easily find out it here. You can do it here. Okay. So how to find out it here? You can save your structure in the XYZ format, and you will get the what is the coordinates. Otherwise, I will show the easiest way how to find out this one also. You no need to do it manually. You can directly copy and paste. I will show that one. Then you just give the enter. Then here you have to mention like uh, type of elements. Here you have given the total atoms. So here you have to give the type of element which are present. Like you just give the C and space. You have to give the 2 times space. Then type another element, hydrogen is there, mentioned, then space. So there is like, consider there is a one more element like oxygen. Then again type oxygen, then space. At the end, you have to mention the 0. Okay. So it indicates that the element, these are the type of element completed here only. That is the indication. This one is a 0. Then hit the enter button. Then here you can mention the what basis set you are going to use. If you are going to mention it directly here also, you can mention directly. Otherwise, you can just keep it as a generic calculation. Okay. And here you can mention what type of basis set you are going to use. Now we are going to use 631G. If you are going to use like 321G, you can just mention it here. If you are going to use some other basis set, we just mention here. Then at the last, you have to type the 4 stars. So it indicates that. So that is the completion of that input file. Okay. So like that, you can prepare the input file for any type of calculation. I hope it is clear to you. Let me check whether the calculation was done or not. Okay. Still it is going on. Okay. So it is already at a 130th orbital. Let me wait. Okay, so now what I will do, similarly, let's consider if you want to perform the calculation at different temperature and pressure, the only thing is you have to mention that. So if you did not mention anything here, it will perform the calculation at room temperature at 298.15 Kelvin. If you want to perform at like specific temperature and pressure, you just mention temperature is equal to how much temperature, space, then pressure is equal to how much, then space, then pH is equal to how much. Let me show one file here. I don't want to save this one. Let me close this one. Uh, yeah. So let me open this like 400 Kelvin. Okay, so this calculation is like 298 Kelvin. Then no need to change anything here. So this is at like 400 Kelvin. Let me open it in. Let me open this folder. So this is the input file. Let me open it in the Notepad plus plus. See here, everything is same. There is no change in all things. The only changes is this much. You have to mention it like temperature is equal to 400.0. It indicates that it will perform the calculation at 400 Kelvin. Space, that pressure is equal to 1.0. Similarly, if you want to give the pH here, space, type pH, okay, is equal to, let's consider if you want to perform the pH at like 9, just give 9.0. Like that, you can just change and you can just use this file for the calculation. So once your input file is ready, you can submit the calculation directly to the Gaussian software. So there is a question from. So there is a question from like Sachin Kumar sir. Processor means already have some processors means like how many CPUs you are going to perform the calculation. Okay. So this is system or like laptop processor. If you are running it in your computer, then you just give your system. If you are running it in the laptop, then you just give how much it is there in the laptop. So where you are going to, let's consider your local machine. Either it may be laptop or your computer. So where you are going to run you are executing your calculation, according to that you have to give. Okay, I hope it is clear to you how to prepare this input file, then how to specify like respect to temperature and pressure, and you can directly submit it. Later, I will show how to submit. Once this calculation was completed, I will show you how you can use this input file directly to perform the calculation also. Still, it is running. So within that time, let me explain one more topic, anything here. So let me close this one. Yeah. So now let me show it here how to find these parameters. See, so very simple. You can all the information you can just find out. You can just save this format. Otherwise, all the whatever the content here it is there. You can create this content by using the Gauss view also. How? Let me open the Gauss view. See here. Once you have given that, let me. I think I need to go to this option. Or let me open this one. See, once your structure is ready, let's consider if you want to prepare the input file for the phenol molecule. Very simple. Once you have done with that, you just go to the click on the calculate and then click on the Gaussian calculation setup. And you just set up the parameter here, like what is the job type, okay, what is the method, title, everything you just give and you just click on the preview button. So once you click on the preview button, here it will show. You just copy this one and paste it on your notepad or notepad plus plus and you can modify. See here already how it is giving that. What is the charge? What is the multiplicity? So what are the different atoms which are present? So what are their x, y, z coordinates? You just copy and paste it here. And here you have to do some modification. These things not needed. Okay. You just copy this thing. So what is the charge multiplicity? You just copy this part, copy and paste it here. Copy and paste. Okay, and here also you will get the keywords. If you want the keywords you can give, otherwise no need to change keywords. Whatever the keywords you can directly type it here. Okay, so like that you can do that. In my, see, the calculation was completed here, so now I will stop it here. Okay, so like that you can find out the XYZ coordinates. Otherwise, if you type it like one by one, it will take a lot of time. So directly you can draw the structure in Gauss view and you can do this one. Let me close this one now. So I hope it is clear to you how to prepare the input file for the DFT calculation manually, then how to prepare input file for a different temperature, pressure, and pH calculation reactions. Okay, so first let me finish this part, this deformation energy and formation energy calculation. Later I will show you how you can submit that calculation. Once your input file is ready, manual input file, then how to submit this calculation directly to uh, Gaussian software. Okay, let me close this one. Okay, I will just open the Gauss view. See, the calculation was done successfully. Let me, yeah, just click on the S button and let me open this this file. Let me click here, OneDrive. Okay. And let me click on the open button. So now it will give the what is the, so this is the optimized structure here. And now just right click and go to the results, then go to the summary. And it is giving the energy is this much, minus 307.49306. You can just note down this energy value. Okay. So how much you are getting? 307 minus 49393. Okay. So note down this energy value. And now what you need to do? Uh, okay. Now we just close this one. Now similarly, you just draw the structure of, otherwise, what I will do now, so now to just reduce the time, okay, just to reduce the time, we need to prepare the this phenol radical, right? So either you can directly prepare the phenol radical structure, you can submit the calculation, but it was taking a lot of time to for the phenol. So what I will do, just to now we have to prepare the phenol radical, right? So instead of preparing the structure from the scratch, what I will do, I will open the logarithmic file of our previous calculation phenol. From there, I will just remove the hydrogen. So then already that structure is got almost optimized. It will take very less time to optimize that one. Okay. So let me file open. Let me open this phenol logarithmic file. Open this one. So if you want to decrease the reduce the time, you can use this structure. Okay. So now I'm not going to alter anything here. Just let me delete this one. So what we need to do, we have to delete this one. Let go it here. I don't know whether it will work or not. I think it will work. So to delete this one, let me view builder, select this one and just delete the head. See, now it is like phenoxide. Sorry, phenol radical. Or you can call it phenoxide also. Yeah, okay. So now it is deleted. Let me see here. And here, like usually when we represent the radical, we'll give the radical symbol, right? Dot symbol. But here, no need to mention here. Even if it is like positively charged, negatively charged, no need to mention. So automatically see, when you draw the phenol, there are total how many electrons are there? 13 atoms are there. 50 electrons are there. And it was neutral, but it was singlet. But here, see now for the phenoxide radical, it was showing the neutral, but is the spin is doublet. Now here you can perform the calculation by giving the charge is 0 and the spin is doublet. Otherwise, you can perform the calculation by taking the spin multiplicity singlet and the charge is -1. Anything. If you are going to use the charge as 0, you have to use the spin as a doublet. Okay. Otherwise, if you are going to use this as a singlet, then you have to use the charge as a -1. So that is the basic thing. I'm not going to talk about the theory part. Okay. Now let me submit this calculation. So if you want, you can just change this one, but without changing these things, alternate to double bond, single bond. Let me calculate the energy value. Right click. Let me go to the calculate. Gaussian calculation setup. Everything is same. I'm not going to change anything here. Let me do it like this calculation only, both optimization and frequency calculation. Otherwise, let me go with only optimization because for frequency also it will take some time. Let me do only optimization calculation. Remaining thing, everything is same. And what I will give, uh, phenol. Let me give it as like phenol radical. Or you can give as a phenoxide also. Let me copy this one, Control C. General. I think concept is clear to you how to calculate the bond association or dissociation energy. And it was everything is done. Just click on the uh, submit button, save button. Just name it as phenol radical underscore app. Click on the save button. Yeah, submit the calculation. So now it will take quite lesser time compared to our previous calculation. As the one atom decreased, one electron decreased, and even we are going to took the only energy calculation. We are not going to perform the frequency, but keep in mind that just to reduce that time, I'm just doing the energy calculation just to show you. But if you are going to use whatever the parameters you are going to use for the reactant, you have to use the same parameter for the product also. Okay. And you just take with your reactant optimized structure and modify that as a product. So then it will take less time for the calculation. So let me wait how much time it will take. So similarly, once it is done, again you need to perform the calculation for the hydrogen radical. Hydrogen radical, it will take very less time because there is only one uh, electron is there. Okay, still the calculation is going on. We'll wait. So if you have any questions, you just write it in the chat box. There is a question from Ankita. Should not we select unrestricted in the method file as it is radical? Yes, if it is radical, you can go with the unrestricted. Otherwise, if you go directly with the default option, software itself, it will decide. Okay, during the calculation, automatically software will consider. So depending on this one, what is the, yeah, even if I think, I think here I did the mistake. I need to check the properties, whether I have given the doublet or not. I think I did not change the properties, I think. Let me check here our previous property. So unrestricted is no problem. That is the default spin. But we have to be very careful while calculating this one, charge and this one. But depending on the structure, by default, it will consider. But I need to confirm that whether it was done or not. So let me click here. Uh, Close this one, right click. Calculate, go to the Gaussian calculation setup. Method, yes. By default, see, once we have drawn the structure, automatically it will consider. Okay. So I has got doubt, so that's why I was checking. Okay, no need, I'll just close this one. Still the calculation is going on. Yes, yes. Yes, it is there. Yeah, usually it will consider whatever the things it was showing here, charge and doublet, it will consider. But it will be good if you confirm before submitting the calculation. Okay, still it is taking more time. Okay, no problem. This is a last structure. So after a hydrogen radical, it will take very less time. So what I will do within that time, so let me prepare our hydrogen radical also. Uh, Let me close this one. I will just close this structure also. Calculation will submit. Let me, what I will do, file, new molecular group. It will add the one more here. Otherwise, let me close this one. Gaussian also. Now the Gaussian is running. Let me open the Gauss view once again. So I'm going to prepare. It is very simple. You just select the hydrogen radical. Instead of modifying phenol, you just draw directly the hydrogen radical. Okay, so very simple. You just go to the view builder option, go to the element fragmentation button here, double click here, choose the hydrogen and choose as a atom. That's it. Okay, so see, now it is hydrogen radical. Usually we'll draw like H2 molecule, right? If you want to draw a molecule, you have to draw the H2 molecule. So here like one atom, one electron, neutral molecule, doublet. Otherwise you can consider singlet molecule charges -1. That's it. And you can perform the geometry optimization of this one. It will take very less time. It will take within like 10-15 seconds. It will submit the calculation, finish the calculation. Let me, this calculation is still going on. We'll wait here. So to calculate the energy, you can just give the parameters. I will wait for that. So this one is still going on. Okay, so within that time, let me talk about any other theoretical part. If I finish the theoretical part, then experimental, like practical, I can show it as soon as possible here. Now let's consider, I have mentioned that one more thing like batch calculation. Okay, so how to submit the batch calculation? For example, let's consider you have synthesized a series of molecule. Okay, and you have to perform the, you have like 20 molecules and you have to perform the geometry optimization of 20 molecules. Okay, and if you do individually, it will take a lot of time. Even if you do the batch also, it will do. But for each structure, you have to prepare the input file, all those kind of things. Here also you have to prepare the input file, but you have to submit again and again. But let's consider if you want to submit all the calculation at a time, like all the 20 molecules optimization at a time, you can do it by using the Gaussian software. It is quite difficult. If you're using this Gauss view, you are submitting the calculation by using the Gauss view, it will take error. You will end up with the error. In that case, you can directly prepare the input file manually, like whatever I have shown previously, and you can just submit your calculation, all the batch calculation. Otherwise, let's consider you have like one molecule A, and you have to optimize that structure at like 10 different temperature, like 300 Kelvin, 400, 500, 600. And for each temperature, you have to do individually, right? And if you want to do the whole calculation at a time as a batch calculation at all 10 different temperature, so just prepare the input file, all 10 input file at different temperature, and you just submit all the input file at a time, and you can perform the calculation. But you just keep in mind that Even if you submit the individual calculation or even if you submit the batch calculation, the time needed to perform the calculation, it won't decrease. It will take the same amount of time. Okay. If you are running it in your like a workstation or supercomputer, in that case you can perform the batch like a batch calculation. But if you're using like normal laptop or like a normal computer, in that case I won't suggest you to perform the batch type of DFT calculation. Better you just go one by one. Okay. So I will show once this calculation was done, I will show how to perform this like single calculation by using the Gaussian directly, and I will show how to perform the batch calculation by using the Gaussian also. Okay, it is taking more time. Let me consider. Within that time, if you have any questions, please write it in the chat box. Okay, so I think there are no question. Within that time, okay, let me show because this periodic system calculation, let me show how to submit. Those who are interested to perform this 2D material DFT calculation by using the Gaussian, for them, let me show how to submit the calculation. So within that time, because I don't want to waste time, so let me close this one. Let me open the Gaussian once again. Refresh. So before that, what you need to do, so I will suggest you to prepare your structure, whatever the 2D material structure is like that maybe like slab structure, like supercell, or you can just make it like a different cloning cleavage of your structure, like a different Miller indices plane, like a 0, 0, 1 plane or 1, 1 plane, according to your requirement. You just prepare the structure either by using the Vesta software or by using the Burai. So both the softwares are free only. Okay, you can download any one software and you can prepare it your structure and you can upload your structure to Gaussian. But now I'm not going to show you how to prepare the structure. Just for the demonstration, what I will do, I will directly download the bulk structure of anything one 2D materials, and you can submit it. Okay, like as a primitive cell, I'm going to submit it, and you know that right, you can download the zip file. In that case, what you need to do, first thing is you need to download the zip file, that is crystallographic information file. So how to download it? There are various databases are there. By using those databases, you can download the structure of your zip file of your structure. Okay, best one is like either you can go with the material project or you can go with the C2DB or ICSD database. Okay, but for this demonstration, let me go with the C2DB. Okay, let me, what I will do, I will just minimize this one. Let me download any one zip file. I will just go to the open Google Chrome and then go to C2DB database. C2DB database. Otherwise, just type C2DB and you just click on this first link here. And you can search. Let me, for example, let me download the structure of molybdenum disulfide. MOS2. And yeah, let me click on the search button. So it will give the MOS2. Let me go with this one. MOS2. Once you click here, it will open the structure. So here from here you can download. Actually, in the day one, I think I have already shown this how to use these things. I'm not going to repeat. You just download the zip file. Now I want to see this is the mono layer. Okay, so this is the 2D structure mono layer of molybdenum disulfide. So you just click on the zip file, then download it. It will save your structure in the zip file. That is like one MOS2, one zip file. Now let me close this one. So yeah, still going on this calculation. Okay, let me keep it here. Now what I will do here. So now to perform the calculation, our zip file got is downloaded. I think it is in the desktop. So just to, let me keep it on the downloads. Let me keep it on the desktop. Control C, Control V. So this is the structure what we have downloaded. Yeah, the Gaussian calculation was completed. Okay. Yeah, but let me finish before that, before going to the analysis part of this one, let me finish this one, how to the periodic system calculation. So once you have downloaded your zip file, now you just open your Gauss view. Double click here, it will open the Gauss view software. Let me, yeah. So once you have opened the software, let me, yeah. Okay. So now you just directly upload the structure. So whatever the structure you have prepared, your 2D slab structure, you can just upload it. So now I'm going to use the bulk structure. What is the mono layer I have downloaded? So I have taken, maybe it will upload to, when I upload the structure, it will consider on the primitive cell. So you just click on the file, go to the open, Now just select the structure you have downloaded, this one, right? Molybdenum sulfide. In your case, you have to prepare the structure according to your plane and see. So this is the structure. So this is the primitive unit cell of molybdenum disulfide. So once you have given your structure, so now no need to do anything. You just submit the calculation. Okay. So how to submit the calculation? So before going to submit the calculation, you have to uh, decide some like periodic boundary condition. If you want to modify some periodic boundary condition, you can use this one. It is very simple. There is one button here like PBC button, right? You can use this PBC button. If you are not able to find this PBC button, it is very simple. You just keep cursor on your structure, right click, then go to the tools, go to the tools, and then click on the PDB option, PBC, sorry, PBC, this one. Periodic boundary condition. You just click on the periodic boundary condition, and here also by using this periodic boundary condition option also you can prepare your structure also. See here the first option, this window will pop up here. The first one is the symmetry tab. Okay, so here you can just give the lattice dimension, whether you want to like only like one dimension x, y, z. So it will give only, see, one dimension representation. So I'm talking about the lattice. If you want like all the 3 dimension, you can select 3 dimension. If you want none, you can just select none option. Okay. And now here, if you click here like lattice type, so what type of lattice type you are going to use? Like triclinic, monoclinic, you can just choose here. Automatically it will select. Okay. And you have to activate this button. Enable space group symmetry. You just check this button. You have to activate this button. Enable space group symmetry, and no need to change here. See here, automatically it will give what is the space group. Okay. Everything it will change. Okay. If you want to change something, you can just do it, but no need to go it here, but just go with the default option here. And if you want to play with the cell, okay, if you want to play with the cell here, then you just click on this cell tab here, and you can just give the parameters like how you want, like alpha angle, beta angle, gamma angle, and then ABC. These are the like cell parameters. If you want to define the cell parameters, even here also you can draw the structure also without uploading your zip file, also just giving the parameters. You can just prepare your structure also, but it is quite difficult. It will take a lot of time. Better you just prepare from some other option, and you can just click here. And if you want to add items or remove items, you just click add this button, and from here you can just do that one. Here there is other options also there. How you want to change here, you can just select it here. And if you want to rotate this bound, all those kind of things, you can just do it here. Okay. And like there is other options are there. I'm not going like axis. If you want to visualize in different axes, okay. And like if you want to delete some part of your structure, you can just use this option, and you just click on the view tab here. Like you can, how you want to represent, like ABC minus A minus B minus C. Like cell replication, if you want to increase, like usually we'll give the space, right? While creating the vacuum along the Z direction, we'll give the like vacuum like 10 angstrom, 20 angstrom. So this is like positive X, positive Y, positive Z, negative X, negative Y, negative Z. If you want to give the upward space, you can just increase this value. You can just increase this value and you can just do it. But let me keep it as like when I'm not going to do anything here. Okay. And if you want to show the boundary atoms, you just click here. See, now it will be showing the boundary atom. Previously, it was not showing only, right? If you want to show the boundary atoms, you can just select this one. See, show the replicate cell. You can just see, you're not going it here. Replicate means here it will just replicate. What is A, what is B, all those kind of things. A, B, C direction. And if you want to show here, you can show it here. And like reference edges, if you don't want to show reference edges, you can just remove it. Okay. And along like how you want to show that, along like X, A axis, B, C, X, Y, Z, you can do that one also. And like position, you can change the position here automatically by default. Here display option is like what kind, how you want to deflate here. Okay, you can just show here, and let me go with the contents here. See here it will give the all the atoms here. So what are the different atoms which are there? Elements. Molybdenum is there. One molybdenum is there. Two sulfur is there. So what is their parameters? Like A value, B value, C value. Okay, like that you can find it out here. And even you can change this modify here. If you want to do modification here, you can just modify also. And if you click here bonds, like rebond, all those kind of things, you can do it here. And you can reduce option is there. And like by using this reduce option, you can just cut it in different plane. Okay, let's consider you want to like for example, already if you are preparing your structure by using this Vesta tool or this one, there only you can just cleave the surface, whatever the surface you want. Otherwise, if you are going to prepare your structure by using here only, then you can give the HKL like 1 1 1. See, this is the 1 1 plane for this one. Like let me keep it as like 0 1 1 plane. This is a 0 1 1 plane. like 0, 0, 1 plane. This is 0, 0, 1 plane, this one. And let me give it as like 1, let me give it like 1, 0, 0 plane. See this like that. So once you have given, you can just, if you want to do that, you just click on the OK and it will just do it here. Okay. But let me, I don't want to do anything here. Let me keep it as like 0, 0, 0 only. Because I'm going to take the bulk structure. If you want to give cleave, you can just use this one and you just click on the OK. So whatever the changes, you just made the changes and you just click on the OK. All the changes will be visible in your structure. So like that, you can prepare your 2D structure for the 2D material structure. Either it may be like some metal oxide, benzene, borophene, graphene, whatever it is. Okay, you have to prepare it. But I won't suggest you to use Gaussian software unless until you are going to run the Gaussian software either in the workstation or supercomputer. Okay, because for this type of calculation, it will take a lot of time. That is the one thing. And preparing your 2D structure is quite difficult by using the Gaussian. But if you are like good in the Gaussian, using Gaussian software, you can prepare it. And the next thing is for 2D materials, we have to use some high level of basis set and functionals, and we have need to use the pseudo potentials. Okay, but in the Gaussian, we have limited number of functionals. We have the limited number of pseudo potentials. Even I think we don't have the option for pseudo potentials here. Maybe limited pseudo potentials are there. Even we have the limited number of basis set in this Gaussian software. But if you go with the quantum espresso, there is large number of variety of pseudo potentials, basis set functionals are there. And if you go with that limited, and those pseudo potential like functionals and bases are like not sufficient to perform the calculation converse, and after like even after like running like 2 3 days of calculation, at the end you will get the your convergence error, your calculation will dead. So the chances of getting error is more when it comes to the 2D material. So that's why I will suggest to whenever it comes to the organic molecules or small molecules or metal complexes, you can go with this one. When it comes to the 2D material surface type of calculation, catalysis analysis, like absorption studies, sensing studies, I will suggest you to use Quantum Espresso or Burai software. Okay, but many people you are like interested to learn like how to submit the calculation. That's why I'm showing this one. So once it is done, but I don't want to do any kind of changes, I'll just close this one. Okay, I hope it is clear to you how to prepare your structure. So if you have any questions, you can just write it here. And now let me show, once your structure is ready, how to submit the calculation. So very simple, same procedure. Click on the calculate button. Okay, and you just go to the Gaussian calculation setup. And once you go to the Gaussian calculation setup, so here the first thing you need to go to the PBC option, periodic boundary condition. Okay, go to the PBC and now you make sure that whether this option is selected or not. You just make sure that you have to check this option. Okay, and now just come to the job type. So now if you want to perform the optimization, whatever the job, you can let consider optimization, select this one. And you can choose like minimum, same thing, no need to change anything it here. Okay, and then go to the method here and you can choose here. What is the ground state here? Okay, so here you can perform the ground state calculation, DFT. See, now only this calculation we can do for this one, DFT, default spin. And you can see here, now better for whenever you come to the 2D materials, the best option is PBE. Okay, so PBE is best one. Functional, and you can choose the basis set, whatever the basis set you want here. And let's consider there is one option here. If you want to perform some kind of like, when it comes to the functional and basis set, functionals we have limited one, but when it comes to the basis set, so only a limited number of basis sets are there. If you want to use some kind of extra basis set, in that case, you just click on the custom button and you have to see here, you can just, yeah, here like there is no option. You just give any basis set. You have to add the list. In that case, you have to go to the changing some setting option, preference option, and you have to add some extra basis set. Okay, and you can do that one. But let me go with just to show 3 to 1G, and you can just select whatever the things you want. Here, let me show here, and the fitting set. Okay, here there is a next option is like fitting set. Here you just click on the auto. Okay, no need to change anything. Fitting set, you just click on the auto here, and the charge, singlet, everything give it automatically. Depending on that, and just go to the title. You can just change the title here. Remaining thing is same, no changes. And one more thing is like you can provide the K points, because whenever we are going to perform this optimization energy DFT calculation of 2D materials, K points matters a lot, right? Sometimes you'll do the calculation at gamma point. Sometimes you'll do that like specific K points. How to assign that one? You just go to the periodic. See here, the K space like integration method. So by default, if you want to perform the calculation at gamma point only, gamma point means like there is a 0 K point. So 0 K point means like 1 1 1 1. And like if you want to do a specific K points, you just click on the specify number of K points and you can select the number of K points. Like 1, 2, 3, 10, how many K points you want to use, you can just do it here. Let's consider if you want to do like 3 into 3 into 3. So usually when you use like quantum espresso or WAPs or those kind of things, usually we'll give like a K point like 1 into 1 into 1. Okay. Or we'll give the K point like 2 into 2 into 2 or like 3 into 3 into 3. So here you can't give like that. You have to give the overall total number of K points. So let's consider if you give like 3 into 3 into 3, how much it is? 27. So like that, you just give the number that. Okay. You have to give that number. I hope it is clear to you. And then you can just preview your calculation and you just submit the calculation. Okay. You just submit the calculation and it will take a lot of time. So, but I'm not going to submit the calculation now. I'll just close it here. So like that, you can perform those who are interested to do the DFT calculation of 2D materials by using this Gaussian, you can follow this method. Okay. I'll just close this one. I hope it is clear to you. So those who are asking for this type of calculation, it is clear to you. So do you have any questions so far? So no additional keywords. Here also for optimization, pop is equal to full. Actually, I have shared like manual to you. So whatever the Gaussian manual is there on the very first day, I have shared that PDF file. If you go through that PDF file, in that PDF file, everything is mentioned, like what kind of keywords if you want to use for the specific calculation. Okay. Like pop is equal to full. You just go through that PDF. I think there are no question. Let's move on to our previous calculation that we are discussing about this so there is a question from Rakesh for 2D composite, how to perform. Similar thing, 2D you just prepare the layer. Okay. You have to prepare the layer, slab material for 2 layers. Like let consider you are going to the doing for like molybdenum disulfide and graphene. Prepare the one layer of molybdenum disulfide, then prepare the layer of graphene, then keep it in one phase and you can submit the calculation. Now upload the structure and you can follow the same procedure. Otherwise, if you want to prepare this one, if you want to prepare the structure directly by using this multiple layer, in that case, there is one layer option is there. This one, you have to use this layer option. First upload your structure, then by using this layer option, you have to add the layers. Okay. So for other dimension materials, example, for that also, for one dimensional, you can use zero dimension materials. Also, you can use same thing also. Like how we are going to use for this periodic boundary condition. Whenever you talk like periodic system, same procedure. I hope it is clear to you, Bhargav. Okay, perfect. Now let me close this one. Now come back to our previous calculation. I think we are talking about bond formation or bond dissociation, right? We are calculating. Let me open this calculation now. So this is the Gaussian calculation. Let me open this one. Yeah, Gaussian calculation is completed. You just click on this S button. Click on the S button and now just open. I think I think backside it is there. Let me minimize this one. Okay. Otherwise directly open. I think it was closed. One. I think it was open twice. Let me open it from the beginning. Let me open the Gaussian software and now just note down the energy value because now we have did the geometry optimization of phenoxide ion, right? We just note down already we note down what is the energy of the phenol. Now note down the energy of the phenoxide radical. So let me keep it here and go to the file, open, then open the logarithmic file of the phenoxide like this one, phenol radical optimization. Click open here, then you just find out the energy, right click, then go to results summary. Yeah, just note down this energy value. So 306, right? So 306. So what is the energy of our phenol molecule? We got 307.4939. So here we are getting the, just note down this value. So 306.8501 minus 306.8501, right? Now similarly, just calculate for the hydrogen radical. So let me close this one, close this one. Just draw the structure of your hydrogen radical already have shown. Go to the element fragment, select the hydrogen, select the atom, click it here, then submit the calculation. Calculate Gaussian calculation setup. Then go to the job type. Let me go with optimization frequency, this one. It will take very less time. Then go with, otherwise let me go directly with the optimization. Optimization method. Okay, let me go with the DFT, default B3L/P 631G plus, let me go with the DDP charge. Okay, double H. Okay, title, let me give it as H underscore opt, H underscore opt. Then go to, okay, copy it, Control C. So the same procedure, that's why I'm going faster. I just want to show that. Just click on the preview button. Yeah, it was done. Just click on the submit button. Click on the save button. Give the name, Control V, and click on the save button. And click on the S button. So the calculation is going on. Yeah, calculation is completed here. Just click on the S button and just select your output file. Then click on the open. And see this output structure, optimized structure. Right click, go to the results, then click on the summary. And what is the energy here? See, minus 0.5002. Okay, so now we know the what is the energy of phenol. We know the what is the energy of a phenol radical, and we know the what is the energy of hydrogen radical. Then how to calculate the bond dissociation energy? Bond dissociation energy is nothing but energy of product minus energy of reactant. So what is our product? Phenoxide and this hydrogen radical. So you just take the two energy values. How much we got? Minus 306. Just let me calculate it. How much we'll get? Let me minus 306. I will just take only four decimal. 306.8501 minus 0.5002. 0.5002. The total energies will get the 307.5, 307.3503. So our this energy is 304. So now we just this minus this one we have to do, yeah, plus this is like 307.49 and 93. So we are getting like minus 0.149. Okay, so that is the energy. We need minus 0.143. So that is the energy needed to break that bond. And that energy is in terms of Hartree. Okay, you can convert it to the electron volt by multiplying that number with 27.21114. Okay, otherwise if you want to convert that value to the kilocalorie per mole, you can just multiply that value into 687 into like 509, that number. Okay, it will give you the energy value in terms of kilocalorie per mole. So that will give the, it indicates that that number indicates that that is the amount of energy required to break that specific bond in your molecule. Okay, and it will result in the formation of two radicals. Otherwise you can tell it like that is the amount of energy is needed to make that OH bond in the phenol. Okay, but it is not like that. For example, in this OH bond we are need this much energy, and you should not conclude that the same amount of energy is needed in case of like ethanol also. In ethanol also OH bond, so it depends on the neighboring group, neighboring atoms, connectivity, all those kind of things. Okay, and here, so what does it number tells? So it like this energy value tells the strength of the bond. It will indicate the what is the strength of the bond. How? Because if the this bond dissociation energy is higher, the value of bond dissociation energy higher, it indicates that the that bond is more stronger. If it is less, that bond is less strong. Okay, so that is the meaning of that. I hope it is clear to you how to calculate the bond dissociation energy or bond formation energy. So any question here so far? Let me close this one. So if you have any questions, please write it in the chat box. So if you don't have any questions, if everything is clear, then type yes in the, like just Y in the chat box, so we can go to the next talk concept. So far what we have done with the scan calculation. We are done with the calculation of salvation energy. We are done with the bond formation dissociation energy. And I have explained like why should we need to perform the DFT calculation at different temperature, pressure, and pH. Then how to prepare the this input file for performing the calculation at this one. And now let me show you how to submit the calculation directly by using the this one, Gaussian. Okay, either it may be individual calculation or batch calculation. Before that, so let me show you how to use the multiple basis set. See, in the Gaussian, when you submit the calculation by using the Gaussian, we can give only one basis set, right? But how to use the multiple basis set? So that is the one thing. So how to give the multiple basis set? And the next question will come, why should we need to use the multiple basis set? Okay. So usually, for example, if you perform the geometry optimization of your metal complexes, let's consider if you have a ferrocene or like a cisplatin, and if you are going to perform the calculation just by using the one basis set, 99% you will end up with the error. Your calculation will die after some amount of time. So why it is like that? So if you want to avoid such kind of errors, you need to use the multiple basis set. So that is the use of the multiple basis set. Why? Because in case of like your large molecule, certain part of your molecule may require more precise basis set, higher level of basis set. Let's consider, for example, in case of like transition metal centers, the center atom will be the like metal, right? So it is like metallic compound. So usually metallic compound needs some higher level, so higher basis set to describe that their electronic structure. So while the surrounding atoms like carbon or hydrogen or oxygen, they need like medium or like lower level of basis set. That is more than sufficient. So we have to use separate basis set for the metallic part, separate basis set for the non-metallic part. Okay. So then you can avoid such kind of errors. Even when you are going to use like 2D materials, if you are going to use like titanium dioxide, like TiO2, it contains titanium is a metal. In that case, you have to use a multiple. You have to use the one basis set for the titanium. You have to use the one basis set for the oxygen. If you use your Gaussian, but if you're going to use with quantum expressor, then no need to worry about those kind of things, multiple basis set. So to avoid this such kind of errors, we are going to use the multiple basis set during the DFT calculation. So now the question will come, how to use that multiple basis set? Very simple. Let me show it here. Let me open one of the input file previously, whatever I have shown. So let me close this one. I will just close this one also. There are some input files are there here. Let me open the first one only. And there is one question from, yeah. So there is previously there is one question from Yamini. So she is asking that, is there any input file which has like doublet? So there is no, but let me show how to, if you want to doublet, how to represent it here. So open with Notepad++. Let me open. Yes. So if it is like doublet, you have to replace this one with the two only. That is the only change. If it is like triplet, you have to replace this one with the three. That is how we are going to represent whether it is singlet or doublet or triplet. So see, this is like only one basis set because it is containing only non-metallic atoms, right? Carbon and hydrogen. Let's consider. So there is a one metallic atom. Let's consider this element has some kind of like zinc. Okay. It has like zinc. Just I'm showing. Okay. Control. Let me mention it here. Just let consider. Just assume that. So there is a zinc metal is there in here in this one. So then what you need to do here, you need to add the zinc also, zinc atom, then give the coordinates of zinc, then give the space. And this one is like this basis set is for the these elements like carbon and hydrogen. And zinc is also there. Then what you need to do here, you just type it here. Very simple, you have to give that. You just type zinc and give the space, then type 0 and hit the enter button and just provide the what basis set you are going to use for this calculation. And usually for the metallic atom, what I suggested, if you are going to use the Gaussian software, this LAN L2DZ is the best basis set for that kind of thing. And you just type this one, LAN L2DZ. Okay, just type DZ and then hit the enter button. Again, you have to give 4 stars. Star, 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 star. It indicates that that is the end of that, this one. Let's consider your material has like two metallic atoms. And if you want to use the two different metallic basis set, in that case, if you want to use like 3, again, you just give the enter. Okay. Then again, give the enter. Then you just type again. Let's consider you have the titanium. Titanium, space, give the 0, then give the enter. And let's consider if you're using some other. Like for example, for this one, if you're using, just I'm showing, if you're going to use like 6, 3, 11G, and then hit the enter button and then give the star 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 star, and you just save this file and you can submit this for the calculation. So like that, by doing this kind of modification in your input file manually, you can perform this geometry optimization of large molecules or metal complexes. So this is highly useful, especially when you have the doing the optimization of the metal complexes, especially there is a like metallic atoms. Okay, but you have to do it manually because Gaussian won't create this input file for the multiple basis set. It will go only for the one basis set. I hope it is clear to you. So how to use the multiple basis set? Okay, now just let me close this one. No, let's close this one. Yeah. Okay, now let me show, I will just choose this one. This is the input file, Control C. I'll just keep it here, Control V. Okay, so this is the input file, right? So let me open with Notepad once, Notepad plus plus or Notepad, anything. Let me open this time like Notepad. Previously we are open like Notepad plus plus. Yeah, you just click here, open. So this is how it looks like. So this is your input file for the optimization plus frequency calculation of methane, CH4. And if you want to submit this kind of like consider you have prepared this input file, and if you want to submit this file for the calculation, let me close here, close here. Okay. In that case, what you need to do, you just directly submit the calculation. Okay. So here, open, let me, I think there are some question. So draw the structure and copy the coordinates and do the required changes for the material. It will take time. Okay, we already shortage of time. Okay, you just draw the structure and you can just copy it. I'm just giving the idea, so it will take a lot of time for that. So I'm not going to do that one. If you want, you can just draw the structure and you can just copy and paste it, and you can just do the modification if you want. Okay, so now let me. So, okay. So you're asking whether I can do it or not, like that, draw the structure and copy the coordinates and do the required changes for my, yeah, that is a procedure what you have to follow. If you give the coordinates individually, it will take a lot of time. Let's consider you have the metal complex. And yesterday also someone asked like how to draw the metal complex. Let me show it here. So better I will just clarify because I don't want to go with some doubts. So let me see it here. Let's consider if you want to draw some metal complex, just let me show it here. Uh, I will just go to the element fragment here. Let me choose iron here. Let me, yeah, anything. Let me draw some kind of like rhodium. Otherwise, let's rhodium. And like here you can choose what kind of metal complex, whether like tetrahedral, like octahedral, what kind of you want to plot this one. Let's consider rhodium. Just this got rhodium got selected. So now at the center is the rhodium here. And if you want, let's consider if you want to replace all this with like chlorine, hexachlorodium, then what you need to do, just go to the again element fragment button, select the chlorine. Let me select as atom, just select replace this one. See the chlorine bond is changing. See hexachlorodium. So there are total 7 atom, 147 electrons, neutral molecule, doublet. So because doublet, why it is like -1 charge, so that's why it was taking the doublet. Yeah, you can just take it here. Once it is drawn, once your like metal complex is ready, here no need to assign charges like -2, +1, -1 like that. Automatically it will consider it here. And you just click here, you just go to the calculate, Gaussian calculation setup. Let me go with just optimization method. Yeah, let me just to show, I will just go with this option only and just click on the preview button. And see, you just copy this one. So this is the charge, and this is like spin multiplicity, rhodium, all the chlorine, the coordinates. You just copy this part, and now whatever the basis set modification I've shown you, you just follow that procedure. So now I think your question doubt is solved. You can follow this method also, and I have shown you how to draw the metal complexes also. You just take the ready-made template and you can just modify according to that. It is very simple. Let me close this one now. So any other questions? Okay, so if there are no question, let me show now how to submit the calculation. Once your input file is ready, how to submit the calculation directly to the Gauss wave. In this case, you no need to open the Gaussian software. You directly open the uh, Gaussian. Okay, you just double click here and it will open the software. Now this time it will open only the Gaussian. So this is the main Gaussian software. I think I can't increase. Okay. Okay. So now we can submit the calculation. So how to submit the calculation? To submit the calculation, here you just there is a click on the file menu. Let me keep it here. Now you just click on the file menu. So once you click on the file menu, you will get this option. So here you just click on the open. Click on the open. So once you click on the open, it will be redirected to your file manager. So now navigate to the folder where your input file is present. In my case, it is present on the desktop. I will go to the desktop and select the Gaussian input file. So this is our Gaussian input file, ch41. Select it and click on the open button. So once you click on the open button, see it will upload. So what kind of calculation? So what is the root section? What title? What is the charge and multiplicity? Okay. And see here different coordinates, basis set, everything. So everything is uploaded. You just click on the OK button. At the right side, see there are two options. There is first is OK button, next one is run button. If you want to submit the calculation, you can click on the run, or let first click on the OK button. If you want to directly run the calculation, you just click on the run button. Otherwise, if you want to go step by step, you just click on the OK button. It will upload the file. Okay, you just click on the OK button. So once you click on the file, see your file got uploaded. This one, see here, active job. This file got uploaded. GIF file, input file, and like ready for the processing to start. Now to start the calculation, very simple. You just click on this button here. That you just click on this button, it will start the calculation. See, and now once you click on the start button, it will ask you to save your output file. How you are going to save your output file and where you are going to save it. Let me save it on the desktop itself. I will just save it as a demo. I will just save it as a demo Gaussian output file, and you just click on the save button. See, the calculation is going on. So this is how you can submit the individual calculation directly by preparing the input file and directly submitting to the Gaussian software. I hope it is clear to you. I don't know how many of you are doing simultaneously with me. So there is a question from Rakesh. Can you show and explain, if possible, how the DFT data explained in literature paper? See, DFT is a vast subject. Okay. So depending on the application, you have to explain. So while doing this throughout the lecture, I'm just explaining each part. So how to analyze your XRD data, like sorry, your FTIR, how to analyze the UV, how to analyze the NMR or like optimization. That is the explanation. But the thing is that you have to correlate with that your application. The way of like presentation, it will be changed depending on the what you are going to correlate. But if you want, I will just show download on any paper I will open. At the end, I will explain you. No need to worry about that. Okay. The calculation is, yeah, the calculation was done here. See, once the calculation was done here, in the Gauss view, you will get the message, right? The job got submitted, whether you are want to open or here, it won't show like that. Okay. So once the calculation was done here, so you like here it will complete, it will show here processing complete. And at the end, you will get this some quotation here. And it will show like how much time it took, all those kind of things. Now we just close it here. And now this is our output file, demo.dat. So now see, when we run the calculation by using the Gauss view, it will generate two files, right? Logarithmic file and CHK file. But when you run the calculation directly by using the Gaussian, it won't create the two file as a separate file as a log and CHK file. So whatever the information is there in log file and CHK file, it will keep as a one single file. Okay, as a your output file, Gaussian output file. And now we can just open it in the notepad and you can do all the data information. You get all the information. And if you want to plot the graph like optimization curve, in that case, again, you need to open this one. See here, like different calculations are there. You just open this file in the your Gauss view, same procedure. Open the Gauss view, then go to the file, then open this file, and you can do the analysis, the same procedure. I hope it is clear to you how to submit the single calculation. Now let me show how to submit the batch calculation. The same thing, if you want to perform the multiple calculation at the same time, if you want to submit it, then how to do this batch calculation, right? So here what I will do, so this is the one. I will just select three file, 2 or 3 file. Let me go with this here. So let me select here also this input file also. So I will just rename this input file as CH42. I will just rename it as CH42. Okay, just go with the 2. Okay, that is more than sufficient for the demonstration. You have to follow the same procedure. Let's consider now I am going to submit the multiple. So just for the demonstration, I'm going to take 2. Even if you want to submit 100 job, you have to follow the same procedure. Okay, so you have to prepare, let's consider you have the 10 molecules, and if you want to perform the geometry optimization of 10 molecules. In that case, what you need to do, just prepare the input file of all the 10 molecules and upload those file and submit the calculation. But the procedure will be different compared to your individual. There is a slight difference in the uploading files. Let me show how to do that one. Okay, so for that, what I will do here, yeah, open the Gaussian now. First, open the Gaussian software. So once you open the Gaussian software here to submit the calculation, so when you submit the individual calculation, we are going to open the file and we are uploading, right? But when you are going to upload your batch calculation, we have to use the utilities. Okay, you just click on the utilities menu, and here just click on the edit batch list. Click on the utilities, then click on the edit batch list. Okay, so once you click on the edit batch list, this window will pop up here. Okay, and here what you need to do to add the input file, you just click on the add button. Click the add button. So once you click on the add button, it will be redirected to your file manager. So now just navigate to the folder where your input files are present. So for to avoid the confusion, you just prepare the input file and keep all the input file in one folder. But in my case, it is present in the desktop. I'll just go to the desktop here and let me select it. So these are my two input files, CH41 and CH42. And let me select this. You have to select one by one. Okay, you can't upload multiple files at a time. Select one input file and you just click on the OK button. So once you click on that, it will show that how you want to save your output file. You just give the name of your output file. Let me, I just save it as a, what I will do, demo 1, I will just save it as demo 1. For CH41, I am saving it as a demo1.out. Click on the OK button. See, it got uploaded here. And if you want to add the more files, again click on the add. Then again select your file, this one. Click on the open. Then you just give, for this one I will give the demo 2. Demo 2. And click on the OK button. Like that, if you have like 20 input files, just click on the add button. You can just upload it. Okay. I'm just, for this demonstration, I'm just going with the 2. Okay, so once you have uploaded like all the input files, what you need to do here, like select reorder, set start, okay. Think, okay. And you just click on the reorder, and you can reorder also. So by, see here, like if you are like first file, first it will execute this calculation, then execute this calculation. So if you have the preference, like you want to do the like emergency for the one particular molecule, you can reorder it also. By using this option, you can reorder. Okay, and now here you just click on the I think you can, I think it will upload it file. Yeah, it is uploaded. You can just here you just click on the file now. You just click on the file. Once you have done with that, you have to save this one. To save this file, so here you have to click on the file. See, don't make confuse. Here also the file folder is there. Here also is there. To save this file, whatever the file you have uploaded, because now we are going to upload the individual input file. So once you uploaded all the individual file, you have to save all the individual file as a one input file, one batch file. So to save as that batch file here in this window only, that edit batch control list, you have one more tab here like file tab. You just click on the file tab here and just click on the save button. Okay. I think, yeah, select, I think, yeah, click on the save as, and here you just give the name. So where you want to save, you can select the folder. I want to save it on the desktop. Let me give it as like batch only. I will save it as a batch file. Batch, okay. And just click on the save button. So now the file got saved and you just close this one. Our batch file is ready now. See, the batch file is got uploaded here. Whatever the batch file you have saved here, it got uploaded. So I think there is some question here. So there is a question from the Amini. Can we do it for the earlier example of phenol, phenoxide and hydrogen as a batch file? Can we upload? Yes, we can do that. Yeah, that is the beauty of this calculation. Instead of that, you just prepare the input file for your different whatever the things you want, and you can just upload it directly. But the time, it will take the same amount of time, but it will do the, no need to again upload, like submit again and again. at the one stage it will perform the calculation for all the three. You can do that one. Now here, yeah, we are done with this one, right? Okay. So now you just click on the file option. So this is a batch data. Again, you just click on this now file here. And now here you just click on the open. And now you select your batch file. Whatever the batch file you have saved here. Let me find it out where it is. Yeah, this one, batch.bcf. You just select it and you just click on the open. Okay. And you just click on the close button. See now ready batch processing start. Okay. So now it was ready to start the calculation. Now to start the calculation, same thing. You just click on here. Click it here. So it will perform the calculation. So once the calculation was done, it will create separate output file for individual molecules. See here, demo 1 and demo 2 output file it got created here and it will save. See the processing complete, calculation was done. You will get the quotation here, the time here. So now you can just see demo file here. Either open it in the your notepad or you can open it in the Gauss view and do the analysis here. So like that you can submit the batch calculation. So open with the notepad. Yes, this one. So like that you can do that one. Okay. So I hope it is clear to you. So now let me wait. What are the things still it is left? Let me delete these files now. We don't need this one. Even I don't want this. I don't want this. Yeah. Let me check that. What is there anything left or whether you have covered everything? So we are already late by 12 minutes. I think yeah, we have covered this day 3. So we are left it, yeah. So we are done with the calculation of salvation. Yesterday we have done till here. And we have done with the calculation of salvation energy of a molecule. We are done. Then bond formation, dissociation is done. Calculation of Gibbs free energy of a chemical reaction. It is the same thing. Gibbs energy is nothing but the overall energy. Like if you want like chemical Gibbs free energy, same thing. Like you can calculate the energy of your reactant and energy of your product. Can do that. Same thing. So there is no extra thing for that. You just draw your reaction for individual molecule. For example, if you want to calculate the Gibbs energy, free energy for your individual molecule, automatically after geometry optimization and frequency calculation, in the summary option itself under like a thermoelectric property calculation, you will get that. Already have shown this one. If you want to do it for the chemical reaction, then you have calculate separately for the reactant and product and you can just upload it in the formula. You will get it. And we are done with the DFT calculation at different temperature pressure. We are done with the how to use the mixed or multiple basis set done. Batch DFT calculation done. And we are done with stability yesterday. We are done with PS. So now we are left with this one. So intrinsic reaction coordinate calculation. Okay. So by performing this intrinsic reaction coordinate calculation, you can find out what is the transition state. Okay. More like, which is like more preferable transition state for your reaction. So what is the path of reaction? You can explain the mechanism of reaction. So, but to perform this one, it will take at least like 1 to 1.5 hours. So what should I do? Are you ready to listen it? Like IRC calculation. So I will give you two options. So if you are ready to listen it, I will just continue it for another 1 to 1.5 hours. Okay. So if you are not ready to listen it, I will just make the recordings. Okay. I will just share the recordings. I will do the recording for that part. Then I will share the recordings. So you have to just respond fastly. So whether you want to watch it as a live or you want recordings, please write it in the chat box. You just write it in the chat box, whatever you're feeling inside your mind. Okay. Okay. So Subhash is telling recordings. What about others? You have to write it fastly. Okay. Recordings. Okay. So what about others? Alright, there are 20 members in the meeting. Okay. So okay. Recording. Okay. Okay, so most of the participants, because those who are responding, they're asking the recordings. Okay, I will share. Okay, whatever you're listening, the same thing, whatever the recordings I have shared so far, such kind of recordings only will get. like step-by-step explanation. You just practice it through that. Okay. And here I will share because it will take around like 1.5 hours. I will give the recordings. And like yesterday, I think some student they have asked some question. If you want to learn something extra new, you just write it in the chat box, any specific thing. So if it takes less time, then I will show it here, and within like 10 minutes. And yesterday, one student they have asked like how to calculate this fluorescence spectra. Like fluorescence, if you want to calculate absorption uh, of like emission spectra. In emission spectra, there is like two type, right? You can calculate is like fluorescence, and we can calculate it as a phosphorescence. Two phenomena will take place. So when the fluorescence will take place, fluorescence means like singlet to singlet transition. Phosphorescence means triplet to singlet transition. Whereas like absorption means like singlet to singlet transition. So it is very simple. The same procedure, whatever the procedure you have followed for the, let me show it here. Just I will show you. Don't run the calculation. Just I will show it. Those who want that calculate this absorption spectra, emission spectra. In that, if they want specifically like fluorescence and phosphorescence, let me show it here. Just open the Gauss view and draw the structure. So let me just show it for the methane here. Just draw the structure. Let's consider for this one you have to calculate here. So once you have drawn the structure, first thing is you need to perform the geometry optimization. So once the geometry optimization was done, you just open the optimized structure, then go to the calculate, then go to the Gaussian calculation setup. Then you have to choose the energy type to calculate the absorption or emission spectra. Emission means both fluorescence, phosphorescence, and select the energy. Then go to the method, select the time dependent calculation, time TDSCF, then select your DFT calculation here, default spin B3L by P. You just choose the same option, whatever the option you have chosen here. Okay. And here, charge singlet. Okay. So number of states. Okay. Number of states you can just see here. If you go with the default option, it will calculate your UV spectra. Okay. And if you go with the singlet, okay, singlet to singlet transition. Okay, if you go with the singlet to singlet transition, it will give the absorbance spectra, like absorption spectra. If you go with like singlet to triplet, okay, singlet to triplet, if you go with like singlet, this is like singlet only means singlet singlet transition. Okay, and if you go with like singlet and triplet transition, it will give the transition between the triplet and singlet molecule. You choose particularly this one. Or if you want like triplet only, you just give this one. According to that, it will create the spectra. So for how many days will software work for? Okay, it will work. I won't tell, it will work. Maximum time. Let's consider like 3 to 5 years. So if you use it in a proper way, it will work. Yeah, so here you can choose like, okay, like whether singlet state or like triplet state, singlet and triplet, and you can go with according to that. Okay. So like singlet, if you select only singlet, it will give the absorbance, like absorption spectra. You go with the singlet and triplet, it will give the your emission spectra. Okay. So like that. Otherwise, if you want to, and you have to give here like solve for number of state, you have to select this one. Okay. You have to activate this button. If you want, see, if you directly go with this option, if not activating these two option, if you directly go with the default or singlet or triplet, it will give only the UV spectra only. In UV spectra, it will give all transitions, singlet to singlet, singlet to triplet, triplet to singlet, everything it will give. Okay, even if you go with the default, everything it will calculate. But specifically, if you want to calculate the absorption and emission spectra, in that case, first you have to choose for absorption, you just select the singlet only, then activate this button, number of states. You can go with the 6, or you just go, if you want to more states, you can just go with the 10 or 20 like that. And then you have to mainly have to activate this one, state of interest. So root is equal to 1 indicates that it will give the first absorption band. So absorption means like there is like different, like first, second, third. If you want to calculate the first absorption, you just give 1. If you want to calculate the second one, give 2. If you want to calculate third one, give 3. Usually we'll focus on the first one only. So usually go with the 1. Similarly, if you want to calculate the emission, okay, in that if you want to calculate the triplet. So triplet means singlet to triplet. Here it will select singlet only means the transition is from singlet to singlet. Okay. If you go with the triplet, it will give only triplet to triplet transition. If you go with like singlet and triplet, it is like singlet to triplet, okay, or triplet to singlet, that transition. For emission, you just go with this one, singlet and triplet. Both it will show singlet to singlet, singlet to triplet also, all those kind of things. You just go with for this one. and select this one and you just change this option. It will calculate the emission spectra. I think Samruddhi, someone asked, I don't know, remember exact name. So one or two students, they have asked like how to calculate this kind of studies. Okay, so this is how to perform this absorption or emission spectra. Okay, emission means both things will come, fluorescence and phosphorescence. Fluorescence means you have to calculate singlet transition, we have to focus. Phosphorescence means you have to focus like singlet triplet transition. I hope it is clear to you how to calculate this absorption and emission spectra. Even you can calculate the EPR, so electroparamagnetic spectra. Okay, so there you can just for that I think here we don't have the option for EPR. You can just let me check it here. If it is not there, you can directly give it as a input file. So I think here we don't have. Yeah. So in that case, those who want to calculate this EPR spectra. Okay. So this electron paramagnetic resonance spectra. Okay. So there is a question from Amini. How much approximate time will it take for an ethanol? For what kind of calculation? So emission. Okay. For emission, it will take around 2 to 3 minutes. It will take like 2 to 3 minutes for emission. It depends on like how many number of states you have chosen. If the number of states is limited, it will take less time. As the number of states increases, uh, the calculation time needed also increases. Okay. And I think I'm talking about EPR spectra, right? Electron paramagnetic resonance spectra. Or you can call it as like ESR spectra, like electron spin resonance spectra. So why we'll use this one? It is used to study the materials with like unpaired electron. If you want to study like free radicals or transition metal complexes, that usually will do the like EPR spectra calculation. In that case, you can just prepare input file manually. It is very simple, like the same thing, whatever the input file you are going to prepare. So only one change you have to make. Let me show it what to how to do. Close this one, close this one. So here, let me open okay, any of input file here, anyone. Go to here, yeah, open with notepad plus plus. Open, okay. So the only thing is you have to change this line. So here like you can choose the basis set, whatever the basis set, generic calculation, everything. You just give this command. You have to write it as those who want to calculate this EPR spectra. So before that, first you have to optimize structure. Whatever the calculation it is, the first thing is you have to optimize. Once the optimization was done, you just for EPR calculation, you can just do it here. Like type SCF, like self-consistent calculation is equal to, is equal to tight, TIGHT in capital letter, space, then type property uh, is equal to EPR, or you can EPR, or you can write ESR also, but mention better software will detect EPR. You just type EPR and then space, and again you just give pop. Pop is equal to like population is equal to in bracket you just mention the minimum. That's it. And you can submit the calculation. It will calculate the EPR spectra for your compound. Similarly, if you want to calculate, prepare the input file for directly for like emission spectra and absorption spectra, same thing. You have to give it here. You just write it here like how many in bracket, like let me show it here in the second line. You just give the same thing here. After that, from here, let's consider. So from here, it will change. So you have to give like TD indicates that time dependent DFT calculation is equal to in bracket n states is equal to like let's consider you are going to give the 10 states, comma, then you have to mention the root, like how many, which emission or which absorption you want to calculate. The first one is you just give one, second one is second one, you just close the bracket. Okay, then space, then provide the here, yeah, directly root, it is done. Then you can just space, then give int is equal to uh, superfine, you just give superfine, then space, then you have to write empirical dispersion, empirical dispersion. dispersion is equal to GD3. Like that. This thing is common. You have to give common means you have to just give what kind of function you are going to use, generic calculation. So this is for the your absorption calculation. Okay. So similarly, if you want to calculate like emission, specifically fluorescence, here you have to mention that. Otherwise, like specifically like in, so this will calculate for the this one overall like absorption. If you want to calculate for the emission specifically, then you have just give it only singlet state here. In that case, you just mention as a singlet. Singlets. If you want to calculate the triplet state, then replace the singlets with the triplets. Okay, so this is how we can prepare your input file if you want to prepare manually. So otherwise, let me EPR also, let me check. I think one thing, let me check it here whether it is there or not. Input file preparation here directly by, you can run it by Gaussian. Let me go with this option. Go to the calculate, Gaussian calculation setup. Go to the pop here. EPR. Okay, perform NBO calculation, NBO. I think SCF. I think we don't have like directly, we can't think here. I think there is no option is not there. Yeah, in that case, you just prepare your input file manually and you can just let me write it PDB max. Okay, geometry, no here. Okay, so for EPR spectra, those who want to calculate this electron paramagnetic spectra, just follow that procedure and you can just prepare the input file and you can submit the calculation to the Gaussian. So I hope I cleared all your doubts. So if you have any questions, please write it in the chat box. I'm just already we are late by 30 minutes. So if you have any questions, please write it here. So you have like 5 to 10 minutes time. Within that time, if you have any questions from day one, you just ask it now. Okay, thank you so much, Subhashri. So any question? Okay, from Aminisa, do we have all these GIF file in manual? I think maybe. I don't know. I'm not sure, but maybe I think you will get. At least there is some idea like how to select. I think it will be there. So I did not go through the manual properly. Maybe it will be there. You have to check it once. I'm not sure. Any other questions? Okay, if there are no question, I'm going to end the meeting. So, so can you suggest a way to learn this input file preparation? So I think the format of input file preparation is mentioned it in the manual only. You just go to the Gaussian website. From there, you can do that one. So from Subhashi, one small suggestion for the theory, if you could explain through PPT, it will be better to understand. Definitely, Subhashi, from next time we'll try to explain it the PPT. So like commands and all. Yes, it will be in the manual only, but it is not at a one place. So it is like, I think that manual is around like 200, 300 page manual. So some part is mentioned in some part, it is not at a one place. You have to go through the entire manual. So any other questions? Okay, thank you, ma'am. Okay, if there are no questions, I am going to end the meeting. Okay, then I hope you learned something from this workshop. Okay, so we have covered whatever the things we have mentioned it in the brochure. We have covered everything. Okay, so thank you for your participation. I will share the recordings of today's session and I will share the recording of that IRC calculation also within 30 minutes. And I will share the feedback form also. You have to submit the feedback form. So once you submit the feedback form, you just check your email you to download the your participation certificate. Okay. So thank you so much. Bye bye. Good night.